Thank you, Sharif and Paul, for the invitation to speak here today. I regret that I am unable to join you in person, but I'd like to talk to you about what electron density analysis tells us about bonding in transition metal doped boron and carbon clusters. Well, why boron? Boron has several interesting and unusual properties such as small covalent radius, the electron deficiency, and a higher coordination number than its formal valency. Boron atomic clusters show several interesting and unusual size-dependent properties, including aromaticity and a diverse range of structures such as bowls, rings, tubes, quasi-planar sheets, and fullerene-like cages. Smaller clusters with less than 40 atoms generally have planar and quasi-planar structures. The propensity for a particular boron cluster to choose a certain shape changes drastically due to the presence of a dopant atom, which alters the electronic configuration of the system. Let us start with very small, simple clusters of boron in the size range of 3 to 11 atoms. We see here the Laplacian contours of the electron density overlaid with the bond paths, nuclear, bond, and ring critical points as determined by Amol. We see here plots of the electron density versus Laplacian at bond and ring critical points for both neutral and anionic boron clusters. When I say peripheral bonds, I mean the ones around the ring. The bridging bonds are the ones across the ring. Radial bonds are the ones connecting the central atom to the atoms in the circumference, and central bonds are the ones wholly within the ring. We immediately see that bonds of similar character cluster together, and also that the peripheral bonds show strong covalent character with high electron density and high Laplacian. We see similar trends in plots of the bond ellipticity versus Laplacian at the bond critical points. The low ellipticity of the peripheral bonds attests to their covalent nature. Thus, electron density and Laplacian at the bond and ring critical points, as well as bond ellipticity, may be used to distinguish different types of bonds, such as traditional covalent bonds, electron deficient, multi-center bonds, etc. We now turn to a study of metal doping of drum-shaped boron clusters. We found boron-14 nanodrums suitable for this purpose, and 3D transition metal atoms best suited as dopants due to their size. 4D and 5D metal atoms, however, prefer quasi-planar geometry. We find high doping and embedding energies for vanadium through nickel. The HOMO-LUMO gaps are the highest for endohedral nickel in B14 and the isoelectronic cobalt in B14 anion. The structures of nickel and cobalt encapsulated boron nanodrums are symmetric with the boron-boron intra-ring distance less than the boron-boron inter-ring distance. In the case of iron at B14, the iron atom is unsymmetrically situated closer to 1b7 ring. Here we see the isosurfaces of the electron localization function for undoped and doped boron clusters, boron nanodrums. Only the peripheral bonds appear at the highest ELF contours, which correspond to normal covalent bonds. Lower ELF contours reveal bonds with multi-center character, and these are bonds connecting the two rims. Here we see contours of the Laplacian of the electron density in different planes for nickel at B14 and iron at B14. As you know, the Laplacian provides a measure of the local charge concentration or depletion, with positive L corresponding to charge accumulation and negative L to electron depletion. These plots again distinguish the largely covalent bonds along the rims from the electron deficient multicenter bonds connecting the two rims. Next, we progress from boron nanodrums to boron nanotubes. Unlike carbon nanotubes, not much is known about their boron counterparts. Boron nanotubes were synthesized from buckled boron sheets but were shown to be deformed. An undeformed columnar boron nanotube was theoretically shown to be possible by rolling an alpha sheet of boron. Since Some metal-doped boron nanodrums are highly stable. We asked, can we use one of these stable structures as a precursor for a nanotube? We initially created the dimer and trimer of metal in B14. CO3 in B42 has a HOMO-LUMO gap of 0.17 electron volts and an extremely symmetrical prismatic structure, and it was thus considered as a template for the creation of a nanotube. This led to a boron nanotube with a diameter of 4.36 angstroms, which is the narrowest nanotube of boron to be reported. Here, the interaction of the nanotube with the encapsulated cobalt nanowire stabilizes the structure. Similarly, we have a boron nanotube sheathed iron nanowire. Well, how about other sheathed boron nanotube structures? We use the Fe4 at B56 cluster to generate the unit cell for an infinite nanotube, giving a very different structure, which is shown here. We now move on to endohedral chromium, molybdenum, and tungsten-doped B18 to B24 clusters. We see here the electron localization function isosurfaces for chromium in B20, molybdenum in B22, and molybdenum in B24. Two orientations are shown in each case. The higher isosurfaces, which are shown in purple, correspond to two-centered bonds, whereas the lower isosurfaces shown in yellow correspond to three-center bonds. We see this also from the Laplacian contour plots of chromium in B22 shown here, along with the electrostatic potential of the cluster mapped onto a 0.1 electrons per cubic Bohr electron density isosurface. Here we see the localization-delocalization matrix of endohedral chromium in B22. Looking at the color-coded matrix, it is apparent that LDM analysis reveals different types of bonds with different degrees of delocalization. This slide shows how successively larger clusters may be built up from planar B18 to endohedral molybdenum at B24 cluster. We have also studied doping of larger boron clusters. Here you see the hexagonal B36 cluster with a 6-atom hexagonal 6-atom void, and the same cluster doped with 6 boron atoms replaced by carbons. This has a triangular 9-atom void, and the carbon prefers to occupy peripheral sites. Here we see side views of the same cluster. While the B36 cluster is bowl-shaped with a 6-fold symmetry, doping with 6 carbon atoms increases the curvature and distorts the structure, lowering it to 3-fold symmetry. Laplacian contours of the B36 cluster are shown here in the planes of the outermost ring and the innermost ring, showing covalent bonding along the outer ring and multicenter bonding between the different rings. Here we see the Laplacian contours of the doped B30C6 cluster in the plane of the outermost, the middle, and the innermost rings. The symmetry breaking and out-of-plane distortion are evident, with covalent bonding along the outer rim and within chains in a plane. We have also investigated several B70 isomers, tubular, quasi-planar, and cage structures with different numbers of hexagonal voids. The lowest energy isomer of the neutral singlet has a tubular structure, but a quasi-planar isomer with 3 hexagonal voids is closed in energy and is favored by the anion and cation. Some of the tubular and quasi-planar B70 isomers with different numbers of hexagonal voids are again shown here. We see here the electrostatic potential of the lowest energy B70 cluster mapped onto a 0.1 electrons per cubic Bohr electron density isosurface and the contour plot of the Laplacian in a plane around one of the hexagonal voids. The surface electrostatic potential map and Laplacian contour of the low energy quasi-planar B70 isomer with 3 hexagonal voids is shown here. Plots of the electron density versus Laplacian at bond and ring critical points for both isomers, the tubular and quasi-planar, are shown here, and these show that the peripheral bonds along the outer rim have covalent character with high electron density and Laplacian and can be distinguished from the other bonds. Electron localization function plots of P70 show that only the peripheral bonds appear at the highest ELF contours corresponding to normal covalent bonds, whereas lower ELF contours reveal bonds with multi-center character. So to sum up what we have learned about boron clusters, the Laplacian at bond and ring critical points, the ELF and the LDM reveal the extent of delocalization of electron density and the nature of bonding in boron clusters, distinguishing between different types of bonds, localized covalent two-center two-electron bonds versus three-center bonds and delocalized multi-center bonds. The propensity of boron clusters to take on certain shapes is influenced by doping. The small boron clusters with less than 20 atoms adopt planar or quasi-planar structures. The smallest size of boron clusters to form doped nanodrums is B14. The correct transition metal atom for creating stable doped drum clusters is a 3D transition metal atom from chromium to nickel. We see that carbon prefers peripheral sites. Drum clusters show two-center sigma bonding within each ring and three-center sigma bonding between the rings. M and B14 clusters form stable nanotube assemblies. And as we see here from this plot, the internuclear distance parallels trends in the electron density at the bond critical points. This plot contains data from all the boron clusters studied. Next, we look at carbon clusters. We know that small carbon clusters prefer quasi-linear chains in 2D structures to minimize strain and decrease the number of dangling bonds. Even-numbered chains prefer closed rings, while odd-number structures prefer open chains. Strained carbon clusters such as C20 can be stabilized by doping with a transition metal from the first half of the 3D series. So we doped the systems, the carbon clusters, with a 3D transition metal atom from scandium to iron, choosing a ring of the correct size to accommodate the metal atom and sufficient overlap to contribute to stability. Parameters were optimized for the smallest species possible to accommodate a single metal atom, and we find that the formation of clusters is governed by two competing factors, strain on the ring and the energy gained by doping. The stability and properties are also influenced by the number of valence electrons in the cluster, the symmetry of the system, etc. Here we see Laplacian contours of the C10 cluster as generated by AMOL. C10 has a planar structure with 5-fold symmetry and a HOMO-LUMO gap of 5.7 electron volts. And here are the Laplacian contours of C10 doped with different metal atoms from scandium to iron. Laplacian contours of the C10H2 cluster are shown here. The HOMO-LUMO gap is 4.14 electron volts. The table shows integrated atomic electron populations, localization and delocalization indices. As you know, the localization and delocalization indices are obtained from double integration of the Fermi hole density over the basins of a single atom or of two different atoms respectively. We see that there are three chemically unique kinds of carbon here. Hydrogenated carbons, which are these, shown in green. The dehydrogenated carbons adjacent to the hydrogenated carbons, shown in cyan, and dehydrogenated carbons furthest away from the hydrogenated carbons, shown here in yellow. And we see that these can be easily distinguished by the localization indices. When C10H2 is doped with a metal, the metal atom distorts the ring out of the plane. Addition of a metal increases the stability. Doping and binding energies are maximum for niobium, followed by titanium. Here we see the Laplacian contours of C10H2 doped with the different metals from scandium through iron. Turning to C9H3, we find that it's a planar ring with threefold symmetry. The lowest energy multiplicity is a doublet. Each carbon atom contributes approximately 4 electrons to the ring. There are two different symmetry equivalent types of carbons. hydrogenated carbons shown in yellow, and which are these C1, C3, and C7, and completely dehydrogenated carbons, which can be distinguished by the localization and delocalization indices. In spite of being an odd-numbered system with an unpaired electron, C9H3 has a significant HOMO-LUMO gap of 2.2 electron volts, which we attribute to the extensive electron delocalization in the ring, the strategic hydrogenation of the ring at points of strain, and the symmetry of the molecule. Shown here are Laplacian contours of C9H3 doped with different metal atoms, titanium, manganese, and iron. The table here shows doping energy, binding energy, and the HOMO-LUMO gaps. Finally, we see here the Laplacian contours of C12H3 doped with different metal atoms, as well as the doping and binding energies. So, to sum up what we have learned about carbon clusters, the electron density versus Laplacian graphs show that ring critical points and the metal carbon critical points all lie along the same trend line. The ring critical points have low electron density and nearly zero Laplacian, suggesting a space with low uniform electron density between the carbon ring and the metal. All clusters bind to the metal using coordination bonds and charge transfer. The carbon-carbon bonds are strongly covalent, and the metal-carbon interaction is of pi d type. Let me close by acknowledging my colleague, Professor Sukumar from the Center for Informatics at Shiv Nadar University, my former student Pinaki, and Vijay's former postdoc Amol, who did the work on boron clusters, and my former undergraduate student Rudra, who did the work on carbon clusters. Thank you for your attention, and if we have Skype connectivity, I'd be happy to answer any questions you might have.